right. So the key to the moment distribution with a sway structure is information and using the table. Using the table. Let me kind of get the table first and see if you let me just get the table. The table becomes of important. The table. All right. All right, that is, let me see. All right, I'm going to share the table, and the reason why I'm doing that is for an understanding. All right, you're seeing the table, right? All right, good. The key to this in terms of the different steps in the moment distribution, when you come upon solving the fixed end moment, this is a table that is being applied. The loading on the beam of the table can be in any of these form. You get what I'm saying? The last time we did one in the exam, there was a uniform distributed load. So this is a formula that you would use. WL square over 12 for this side. And the convention, we approach the moment distribution as clockwise. So going into the clockwise direction. If this side is going anti-clockwise from here to here, A to 0, right? Then this becomes a negative. This going into the positive side. So we keep the sign convention, negative and positive. But look at it, look at it. So when they analyze this, it is positive going down. So if you get something like this, you know which of the formula to use in terms of the beam. You get something like this, right? You know A, B. You see that. If you get something like this in terms of a point load in the center, then you use, you understand what I'm saying? So let's go. All right. So if you know, in a case, hide. So in a case like this, look at this. So this is a frame, right? In this case, the load is right here. There's a basically a lateral load of 20, and these are all in. All right, these are all in kilonewtons. All right. So 20 kilo, and this is here is 40 kilo. The distance where this is located is 3. This is 1.5. All right. The height of this is 3 meters, and it's all in meters. Okay. Right. We know what we're trying to find. What we're trying to find, and I'm saying to you, if I don't give you the EVA, the flexural rigidity, right, EI, you can treat this as constant, right? Once it is not given, if it was given, then you apply it in the formula, and so forth. So what we're trying to find, right, is you're trying to find a sway, no sway. So you're trying to find the problem is going to be divided into two parts. You're going to find what I refer to as a sway, right? And no sway, I mean non sway and sway. All right, so that is where we're going. So let's start. So problem one, we're looking at so one, we're trying to find first the, let us find the problem no sway. Is it no sway? Yeah. All right, so no sway. All right. So the no sway, there are some things that you need to I need to establish. Is that these equations may not necessarily given, but the whole concept is sorry, is this. So this we're trying to find is this is m, this is m prime, right? Plus, right? Um, there's, yeah, all right, yeah. I think there's an important factor, which is that, right? So this is m prime dot. So we're saying that this is no sway, all right? Just to kind of, and this is sway, all right? We know that there is, there's a shear, or should I say, a horizontal force here, which is called this H A. This is A. This is B. Use another color. This is A, B, C, D. So if I find H A, H C. So this is the HA prime, HD prime, HA double prime, HA, HD double prime. All right. So one is propped against sway and so on. All right. That's just the concept. So in terms of the sway, no sway. So each of these, so you will establish the equation that we're going to be using. So let me just put it here. So some equation is you take m equal to m sway plus the correctional factor m double prime, right? Then we have the shear at the base, and that is h a plus plus, all right, um, hd plus, this was supposed to be d, um, yeah, and this is d, yeah. double prime, double prime. So this is one, two, three in terms of equation. All right.
Sir,
So
question.
Sir, should it
yeah,
be HB or HA double prime for the
which
second
one
one?
that? This
The
one?
first equation. The second, number
The
two.
second equation.
This one? Which one? This one?
So we have HA equal
Oh,
HA first prime plus XHD double prime. Wouldn't it
mhm.
be A double prime?
This one? This double prime?
No,
No,
sir,
it's
the
the
next.
second one beside it.
You
Yes,
have
that is.
HD double prime.
Yeah, double
Shouldn't it
H.
be HA?
H what? I'm not hearing it clearly.
Sir, shouldn't it be
HA.
HA double prime?
H A H A.
Mm-hmm. Sir, that's an
Oh
error.
yeah. Oh oh yeah. Oh sorry. Yeah yeah.
Okay.
Yes. Thanks. Yeah, because it's all A. Yeah. Sorry about that. Yeah, because it's taking each of these. A yeah. All right. And it's supposed to be all right. Good. So no sway. So we know the shear. Let me just put something here because this becomes important in terms of the shear equation. So the shear equation is the P, right? That is acting, which is a load, right? Plus, right? The HA, which we have established there, right? Plus, this is supposed to be D. This never supposed to have a prime. All right, so this plus that mean D. So that is what we're trying to establish in terms of equilibrium. So let's go. All right. So what we do now is to find sway in no sway. So the first thing is to find what is called the distribution factor. The distribution factor, and the distribution factor is 4, right? For BC joint. So we're trying to find the distribution factor here and here for these joint. So let's go. So so we're saying no sway, find DF, right? For BC. So this is joint B and C. All right. So for joint B, right, we can say, we can safely say it is taken here because what is affecting joint? What are the members in joint A? I mean joint B, the member. So we use this equation. Some person may use 4EI over what again? A 6? 4EI over there's another formula that can be used. Um, I don't recall it right now. But what I use, because if it's EI is constant, then it is I over 3, the 3 which is this here, the length of this, I mean the length of this. Let me just use something else. Let me use another color. So the length of here that we're dealing with. So that's 3, all right? And that is plus 1.5 plus 1 plus 3 is equal to 4.5. I mean, EI over 4.5. I over 4.5. Okay, see that? And when you work this out, right? When you work this out, you you will get, let me see. So when you work this out, you're going to get, you're going to get this. This thing is giving me some little issue. 1 minute there. Let me just see if I can correct this. Lean up. Let me see. All right. So we can safely say 13.5. All right. So this becomes 1.5 AI plus this becomes 3 dot. So this is equal to 7.5 I over 13.5. Okay. So what you do now in finding the, so this, so you add up, so the joints that are so the joint that you're interested in, which is this, which is this joint, you add this length and this length, the stiffness of this and this, then you divide it by, then you divide it by one of the length, which is AB. So let's go. So to find the factor, to find the distribution factor there. So so it would be I divided by 3, right? Divided by, divided by 7.5 over 13. 7.5 I over 13.5. This becomes, after your transpose or you multiply, well, yeah, well, once you divide it, this becomes zero point 0.6. Okay, and this is for B A, because you're moving from B A, so that this is, if that is that, right? Then let me just come right here, right? If this we can safely say, if AB, I mean BA is that, then we could just say CB, I mean BC is equal to 1 minus zero point 0.6 equal zero point 0.4, because this must be 1. Okay, so we can safely say that. And this was for joint B. So joint C now, which is this joint, you're going to do the similar thing. So the similar thing that you're going to do is the stiffness of what connects that joint. So the stiffness is from here, which is C to B. So you say, which is the distance is I, the length has that stiffness over 4.5 plus plus the length here, which is 1.5 divided by 3, right? Again, this now becomes, you can work it out, 7.5 I over 13.5, right? So remember, we're dealing with, so now we're going to find the stiffness of this member divided by the sum of that. That's what it is saying. So the stiffness of, which is BC, so BC, right? I mean, or more CB, yeah, this is supposed to be CB. Let's turn it around, because I'm moving from C to B. So this is supposed to be CB, so that's member CB, right? Is, what is member CB is stiffness. Member CB stiffness is I over 1.4, all divided by the summation of the two members that are affecting that. So I could just easily multiply by 13, 5, 7, that, that. All right. Again, therefore, CD is equal to 1 minus that, and that becomes zero point 0.6. All right. So, so that is it for the finding the distribution factor. After you have found the distribution factor, right? So this is A. After finding distribution factor under the nose way, B, we want to now look at finding the fixed end moment. So fixed end moment. All right. So in finding the fixed end moment, we want to establish our convention, and we already established our convention that anything going in clockwise is positive. And so we want to look at member BC. Yo, do you know why you look at member BC in terms of finding the fixed end moment? The fixed end moments can only apply to where you have a load. If you didn't have a load, there's no need to find the fixed end moment. The fixed end moment there would be basically not. All right. So in a sense, there wouldn't be no sway. There would only be sway. All right. In this case, B, so BC, member BC. So member BC is this. Member BC is this. All right. Remember we said that the 40 is here and this distance is 3. This distance is zero point 0.5. All right. So for the fixed end moment from B, this is B, this is C. So we're saying that the fixed end moment, right? Fixed end moment BC has to be a negative. Let's go back to the, do I have the table? Let's go to the table. Which equation, which of these equation would apply? Are you hearing me? Which equation here so would apply? Good. So that is the equation that would apply. We all clear on that? Okay. So in applying that equation, importantly, so let's go. So that equation becomes, let's go. So we're moving from B, right? So B, so let me just go to, that equation. I want you to note the equation where you apply the square. So if you're moving from here, you apply the square here. If you're moving from here, you apply the square there. You see the square root? The square, I mean, to the power 2, where a square. Okay, so let's go. Because I believe there are some mistakes sometimes. All right, so so this becomes, we understand why that becomes minus. So we're moving from B to that. So this A, right, B square, okay, over L square, right? This is equal to what is the W? The W is 40. What is A? A is 1.5 multiplied by 1.5, and B is 3 square divided by 4.5 square. This you get minus 26.7 kilonewton. All right.
Sorry,
So
question.
yeah,
Why is it that the B square and not the A?
because of how the equation apply. So that is why I was telling you, note it. Let me kind of zoom in a little. So note it. So if you're moving from A, if you're A, which we are at first, then what do you square? You square the part that is further, the divided part that is further away. So that is why you square B. If you're at B, what do you square? You square the A. You get that? See it here. L square over L square. You see that? Do you understand how the formula is applied?
Yes, sir. I was looking at it a different way, but I get it.
Okay. Well, once you look at it at a different way and it's right, then fine. Yeah. All right. So therefore, we now have B fixed end moment for what? So this is a fixed end moment for CB because we're now moving from right to left now. So in this case, let us go back to the let's go back to this. You see this? This is clockwise. So this is why this is positive. I mean, sorry, this is positive because this is clockwise. This is negative because it's anti-clockwise. And that is why we put in a negative value there. So that's why we had a negative value there. So equal, let's go. W, right? A square, because we already established that this is A and this is B. So we square we are further away from where you start, where you want to look at the fixed end to oppose the fx end. B over L squared. This becomes 40 multiplied by square multiplied by 3. That becomes that, no, 5, sorry, square. So this now becomes 26. No, sorry about 26. This is, yeah, that's not it. Yeah, sometimes you get them to be the same. Uh, so this now becomes 13.3 kilonewtons. All right, we're clear on that. So we find the fixed end moment. What do we move on to now? What do we move on to? We now move on to the distribution table. So we see the step-by-step process. So we're going to set up the distribution table. So let's set up the distribution table quickly. All right. Um, so, all right. So this was which one again? This was number. All right. So that's way. All right. So this was part B. What was this? Part B. All right. So let's look at part C. Part C. C. So what is C? The distribution table. All right. So for the distribution table, right? Let's see. I need to get some space. For the distribution table, right? We have the distribution factors. So we have, well, we have the joints, and we could say, we could call, well, let's put this here. All right. We could call that A, call that B, C, D. I mean, I see some person set up some fancy thing, no problem. D, which is this, the distribution factor. This is DF, sorry. So, all right, so the distribution factor, we know there was no distribution factor for, because already it is fixed. So this is 0. So the distribution factor at B, right, we have zero point 0.4, 0.6. Do you understand we get the 0.4, 0.6 based on what we had? We had B, A, B, C. So, so if you go back, based on a distribution factor, right? B, BA, which is 6, and then we did say CB, which is 4. All right. And this now, so this now becomes zero point 0.4, zero point 0.6. Um, this now, the here, this is 0. All right. So in doing the distribution factor, right, we had gotten some the fixed end moment. We already worked out the fixed end moment, right? We already worked out the fixed end moment. All right, so let's go. So the fixed end moment that we had gotten, the fixed end moment that we had gotten, right? What is this? All right, so the fixed end moment just for the beam, which is BC, was minus 26.7, and this was 13.3. All right, this is 0 because there's no, this is a column. These are the columns. All right, based on the structure. Right here we are saying, right, when we, because what we do in terms of the fixed end is like a release and balance effect. So you release, your balance. So if we should go ahead now, right, and say we are going to release and balance the load effect on this joint, right? So we're going to release and be balanced. So when we look at this here, which is a negative, when we release here, in order to basically keep it in equilibrium, this minus, I just rest it here, um, and say 26, and I'm going to apply the factor to this, right? I'm going to apply the factor. So this multiplied by that becomes 16, right? Look at me. So this factor becomes here, because sharing up the loading, or yeah, the moment onto the beam and the beam and the column. So this becomes 10.7. Okay, so that is happening there. Okay, let me just draw a line here to do a carry over. This effect is a positive. So when you release this, in order to keep it in equilibrium, you have to apply a negative 1.3. So that is what we're going to distribute. So if you multiply 13, negative 13, because this was positive, then when you're distributing it, it becomes the opposite of what you had there on the joint. So this now becomes minus 5.3, and this becomes 8. Okay, these are all, right here is 0, right here is 0, because there's nothing to distribute. What you're going to do now is a carryover factor. Is carry over. You're going to carry over half of this. So after you balance it, you release and balance, then you carry over half. So you're going to distribute half of this is 8. This now becomes half of that, so if it says 0, this now, half of this minus 5.3 becomes minus 2.7. So you're basically carrying over, you're carrying over. So this now, this was what, 10. So this now becomes, because it is positive, this now becomes 5.4. Okay? This is 0. This, you carry over this now becomes minus 4, right? So you're basically doing a carryover effect. After you carry over, you have to release again the joint and balance it. So in releasing the joint, once you're going to go into release and balance, then you have to apply the moment distribution table. So here, in terms of the carryover, this, because this is at negative 2, then the factor that you will apply to when you release it, right, to counteract this negative is positive 2.7. So this positive 2.7 is multiplied by that, right? This becomes 1.6. Multiply this by this, this becomes 1.1, right? In this case, right, you are going to do some release and balance as well here, right? So I could keep it here or put it there, it doesn't really matter. All right. So this becomes a negative 5.4 because this was positive. All right. Multiply the factor. This now becomes minus 2.2. This now becomes minus 3.2. And then you're going to do now a carry over. This becomes 0. You carry over this becomes 0.8. Carry over 0, 0. Carry over, carry over this, carry over that. By now you understand the gist, become minus 1. This becomes um, zero point 0.6. This becomes minus 1 point dot. This already is 0. This becomes 0 and things like that. So what you're going to do, you're going to release, you're going to release and balance. In releasing and balance, you got to ensure that you have the appropriate um, signage. Point 1, because this was negative, this becomes positive. You apply you apply the the factor to this, the distribution factor. This now becomes zero point 0.7. This now becomes zero point 0.4. Yeah, this now becomes, well, this is negative 6 because this is positive. Multiply that by that. This becomes minus that, right? This becomes minus 3. 6. All right, this is 0. What you're going to do now, you're going to carry over. They become boring after a while, but that is just the iteration. So this become -4, this becomes 0, this carry over, this become minus point that becomes. So what you're trying to do is to bring it within the 2% of where you have started. This becomes 2, right? This now becomes 0. This now becomes what? Minus what? Point 0.1 that. Then what you're going to do, release and balance. Once you release and balance, what do you mean by release? Balance. Then this becomes point 0.1 that. All right. So you apply the formula here. This now becomes 0.007, right? This was minus, so it becomes that. This now 0. So you apply that. This was a negative 2. So this now becomes negative point that 8. This now becomes negative 0.120. All right. So what am I going to do now? I can now sum my moments. All right. So this summation gives you a value of 9.2, and these are all in kilonewton. This becomes 18. How you know your thing is correct? This must balance. So this, if this is positive, this is supposed to be negative. All right. In this case, this is positive 7. This must be negative because there must be a balance at the end. Yeah. All right. So this is what you have gotten. So remember from the equation, from the from the equation that we establish, right? Right. Um, well, I probably never show you how you get this, but nevertheless, you're going to apply the equation of H. So this is what? C. All right. So this is D. All right. So the equation here, right, is basically it developed from the equation where we have M, we have the moment, right, AB, right, the moment at AB and the moment at plus the, let's see, wait, what is this now? All right, this is moment BA. So basically, there's a moment here and there's a moment, something like that. Yeah, I think it's something like that, where MA depends on the L in the middle and so on. H, L. All right, now. All right. So this is just a column. I'm just showing where it derived from in terms of the moment. So this is what you're gonna apply. LAB. What is LAB? So remember, this is the no sway, which is a prime. This is equal to, which is, we have them here, which we have 9.2 plus 18.4 all over 3. All right. This, when you work it out, becomes 9.2 kilonewton. All right. So you do this part, this, because you're just dealing with the columns only because the moment within the column here as well. So, so that was A. So for D prime is equal to A C D prime plus, oh, sorry, this is not correct. It's supposed to be C. Okay. So what is this? This is minus 11.7 plus minus, yeah, 5.78 divided by what is the length? 3 meters. This becomes minus 5.8 kilonewtons. So that is the thing there in the they call it now the shear in the column. All right, are there any questions? Clear? Are there any questions? We're good?
Not yet, sir.
Okay. All right, hope you're following. All right. So we just looked at problem 1, which is no sway. We're going to look at sway. So we call this 2, and we call it sway. All right. So in this sway, right, we are going to make, you know, uh, we're going to just choose. You could choose any number, but ideally, you want to choose something not too large in terms of the sway in the moment, right? We're going to choose M sway, which is that is minus, all right, 10. So that is our assumption, and we're going to use this to, and we're going to find, right, x, and x is the correctional factor, correction factor. All right. So so we're going to now put this in a distribution table format now. Just as how you did the first one, you're going to be doing it with this as well. All right, so let's go. So the
Excuse me, sir.
sway, say that.
Is there any specific rule when it comes to choosing the sway moment or assuming it?
Normally we assume it with a 10. The reason for that is if you get a big number, by the time you go through the iterative process, it takes so long that you have a lot of iteration.
Okay, sir.
Mhm. I mean, you use 10. Is that something that I've seen used and it's adaptive? All right. So again, you set up your distribution table. All right. So your so which is a table. All right. So again, we have similar joint. No, that one not gonna work. Let's go. So we have the joints. We have A, B, call it C, D. All right. And then we have our distribution factor. This is 0. Carry this up. All right, so for the distribution factor table, we have, again, using the same distribution factor table, 4.6, 0.4.6. So this doesn't change. The only thing that changes is the where you have fixed end moment, you have, I just call it sway moment. So rather than having fixed end, I just call it sway moment because it's no longer fixed, it's more sway. The sway only applies to the column, and that is important. So while the fixed end apply to the beam, the sway apply only to the columns. So that is minus 10, minus 10, minus 10. Okay. All right. So let's get some space. All right, I think initially. So I'm going to release this. I'm going to release unbalance. Let's put it here. All right, so I'm going to release unbalance. All right, so in releasing unbalance, this is 0, this is 0. So in releasing unbalance, then this now becomes positive 10. This multiplied by that gives you 6. This multiplied by that gives you 0.6, 0.4. Okay. Um, this here becomes 0. What you're going to do now, carry over. All right. So do the same thing here. This becomes 40. This becomes 60. All right. This is 0. So release and button, carry over this. This becomes what? 3, 0. This is 4. This becomes 2. This becomes 2 because you carry over. This becomes 3. This becomes 0. Then you do what now? Release and balance. So in release and balance, you release and balance only the joint. So this becomes minus 2. So you multiply this factor, right? This now becomes what? Minus 1.2. This becomes minus 1.8. This becomes, what is this? Minus 2. All right. Apply that. So by now you kind of get a little rhythm. 2, this becomes minus that, that. Carry over. Oh, that become minus. So this becomes 6 minus 6 minus 6. This, can you carry over that? Carry over this, become minus 4, right? This becomes minus 4. This becomes minus 6, 0, 0. This is carry over. You release and balance. All right. Release and balance. So in releasing and balancing this becomes positive zero point 0.4. Yeah, this becomes positive zero point 0.4. Apply that. This becomes 0.24. This becomes what? 0. All right. Um, so yeah, this becomes this becomes 0.16. This becomes 0.16. This becomes 0.240. All right. All right, we're going. So we'll wrap it up. So you do carry over this now. All right, so you carry over. So this becomes 0.12. This becomes what? This is 0. Yeah, carry over. 6, this was 16. This becomes point um, 0.08. This becomes 0.08. So by now I think I should get the juice. Yeah, so it's kind of symmetric. All right, so we release and balance. So release and balance. Come on. This now what? Negative because this is positive. So this automatically becomes negative, which is point dot. Mhm. All right, so we get all of that. Something right here. This is supposed to be 5. All right, that's 5. So we can go ahead now and sum up the, and this is a double prime summation of that. Or this is 0. So this becomes minus 7.5. So summation of this becomes, so we're going to apply the equation. I can do it right here. So I'm going to say equal to m a b b. So this, which is this, 7.5 minus, all right, this is 3. All right, this becomes that. So D, kilonewton. All right. So that is that. So what we're going to do now is to apply the correctional factor. So this is, I think this was 2. All right, so 3. So 3. All right, so we're going to know. So 3, find the correction factor. All right, the correction factor, right, from the equation that we had gotten um, initially, you can go back and look at it, is h a prime plus h d prime, right, which we just got there, plus correctional factor x double prime h double prime plus double prime b plus p. All right, you have to know these formulas. All right, so we already gotten this, which you already know. This is 0.29 plus, no, but this will be a negative here. So this is negative 5, right? That correctional factor minus 42 minus 42 plus 20 equals 0. Okay, so you would have gotten this to be 4 correctional factor of minus 8 equals 0. So to find x, right, therefore, the, so therefore, x is equal to 2.786. So that's the correctional factor. So I apply the correctional factor there. Um, so again, we want to find the actual moment for A, B, C, D. So the actual moment, now, so the actual moment, right? And I call this B. All right. So the correction, the based on the sway and the no sway. So let's go. So we can put it again in a table form. So we have the different joint. So at joint A, at joint B, at joint C, joint D. All right. So we're saying no sway, which is M prime moment, we had gotten at A, joint B, joint C, joint D, right? So we're saying at joint A, we had gotten 9.2, right? B 18.4, and again minus 18.4, 11.7 minus 11.7, and we got that negative. So where we have sway, right, which is the correctional factor m, you will apply the correctional factor. You're going to multiply the correctional factor, which is this, which is 2.786. You're going to multiply that by this in m, okay? So let's go. So in applying that, let's go. It becomes minus 20.9 minus 14, this 14, this 14 minus 14 minus 20.9. All right. Then we have the final, the final joint moment, final. So what is the final joint moment? Add up all of this. So when you add up all of that, this becomes minus 11.7. This becomes 4.4. This becomes minus 25, 7, and this one now minus 26, 7. All right. So this is the final moment. This is what you're going to be using to plot whatever you're going to plot in terms of your diagram. So in plotting that with your diagram, right? So the diagram, just to give you an understanding. So you're basically going to define it based on negative, positive. So positive is clockwise, negative is anti-clockwise. So if I should just draw out the table like that, and I'm saying this figure here, right? This figure here, which is down here, this is going anti-clockwise, so it goes this way. The arrow, the tail is here, so this is 11.7. What becomes of this here? Sorry, let me use another pen. So this here, right? Where does this go? All right, so we have here. Wait, where does this go? This goes positive, so it goes like this. So the tail is here. Where this is going, anti-clockwise. Where is anti-clockwise? Anti-clockwise is heading this way, right? This side now, this one, this 25.12, where is it heading? It's heading positive. So therefore it is going like this. Whereas this is heading, this is heading, which is right at C. This is negative, so this is going this way. This is heading, this is anti-clockwise, so this is heading this way. All right, so this is this here, right? Is C, B, A, D, and we already know that this is 11, this is 4.4, yeah, 4.4, 25.7, 25.7, 26.7. How you plot this? You plot it based on tail. So this is how you plot it. When you're plotting the other thing, when you're plotting it, you have to take into consideration all the loads. So this is plotting the load that is as a result of the lateral loading. All right, but you also have a load which is which is um which is a point load. So if we say tail to tail, then this is a column. So if it is tail, it means that this part is going to go out there. It is more than four, so four is going to project to the tail here, right? This side. All right, so let's go. So let's continue. So this tail is here, so you go this side. The tail is over here, so you go something like that, right? Go something like that. Then this, right? Because the tail is there, then because of the point load, it dips, but it also goes back up, right? So this is the moment that you're interested in. These are the moments. So this is a diagram for the loading on the thing. So this becomes it's 11, 7. This is 4.4. This here, so is there 4.4. This you can work this out by similar triangle, but for now I'll tell you. Um, this is 28.5. All right. Um, this is 25.7, and down here so it's 26.7. Are there any questions? That's it for that. Yeah. All right. All right. All right. I see that you guys are up with me. All right. What next?